So this, we're going to deliver sort of 3 presentations today on different topics. This presentation is on estimating nonlinear population and superpopulation parameters with probability and non-probability samples, and I'm going to get through what all of that is. But while I have it on in my mind, the ABS has offices in every capital city plus Geelong, for those of you who are interested. This presentation today is, these presentations are from sort of 3 individuals. It's all our own words. None of it is ABS policy. Okay, so the background to this issue is that there are high demand for methods that integrate probability and non-probability samples to produce quality official statistics. Now, non-probability samples are samples where we don't have control over the sampling selection mechanism. So one classic example is if you have a data set of tax returns, that data set is going to be missing a whole bunch of low-income people who do not have to submit a tax return. And so when you calculate mean incomes, median incomes, and so on and so forth, they're going to be biased upwards relative to a representative sample of the Australian population as a whole. Probability samples is where the ABS, for example, has control over the sampling selection mechanism. So we can obtain a representative sample that includes those low-income people, for instance. The trade-off, though, is they usually have smaller sample size and less selection bias, but also more expensive. So what we're seeing here is that non-probability samples and probability samples have kind of complementary strengths and weaknesses. So why don't we combine them to get the best of both worlds, both high sample size and low selection bias? Now, such methods differ according to, first of all, the strength of the assumptions used to prove the method, which of the 2 samples includes the study variable, reliance on data linkage. So if you have a survey where people respond with their sort of name, date of birth, sex, address, and you have in tax returns people declare their name, date of birth, sex, address, they might not be exactly the same for those records between the survey sample and the tax returns. So we need to have some kind of statistical estimation process in order to combine the 2. To know which record in the survey relates to the same person as which record in the tax return data set, for instance, the non-probability sample. For use or not of models and auxiliary variables in undertaking the integration, whether and how we account for other errors such as measurement, linkage, and non-response, because how we account for these is going to have implications that flow onto the standard error and the accuracy of our statistics. So that's really important to account for. And finally, 6 parameters that it can estimate, right? Can this integration method can estimate totals and means, or can it also deal with quantiles, regression coefficients, and so on and so forth? I should mention here, because this is an optimization seminar, that where optimization comes into this is that we solve an optimization problem in order to come up with the best way of randomly sampling from the population in the probability sample in order to optimize for the accuracy of the statistics that we're computing. And here are some reviews. The method that we're going to be talking about today extends this method here by Kim and Tam to more statistics. So they deal with means and totals, and we're going to extend their method to a much broader range of statistics. As a result, our method inherits some of their characteristics. So we may have weak assumptions on coverage, so on selection bias. In particular, missing at random is not required for the non-probability sample. And this is another way of saying that we're going to combine things in such a way that even though the tax return data set is biased upwards, we're going to correct for that. So we assume that the study variable is observed in both samples. So we need income, for instance, if that's what we're interested in, to be in both the survey and also in the non-probability sample, the tax return. We require data linkage between the samples, and the other 3 characteristics are different. We don't use models or auxiliary variables in undertaking the integration. We address non-response in the probability sample, but also measurement error, but not linkage error, though we have some ideas about how to extend the method to account for that, including when multiple errors affect the same estimator. So in this literature, what you find is that there are lots of kind of methods that say, oh, let's suppose we have linkage error and solve for that. Let's suppose we have measurement error and solve for that. Let's suppose we have selection bias and solve for that. One of the gaps we're addressing here is, okay, but how do we tie these things together and still compute the standard errors that we optimize to produce our sampling design, our random selection mechanism to go obtain the probability sample? Or how do we produce valid standard errors that take into account all of those things for a scientific study, like so we've got some econometric model or something? And finally, estimates are obtainable when valid estimating equations are available, not just for means and totals. Okay, so I've talked a lot about estimating equations. What are estimating equations? Well, we're going to say basically more or less that everything's either a column vector or a matrix. And here, this is a very classical official statistics setup. So we have some finite population U, that's a set of people, businesses, units, whatever, indexed by some ID 1 through N. For each of the units that we observe a study variable y. I'll get the mouse for this here. Yi here, measured possibly with error as YIA for our probability sample, so our survey, or YIB from our non-probability sample, so our tax returns. And what makes this a probability sample is that this set SA here is random according to precisely the mechanism that we choose. And we also suppose that we observe some auxiliary variables across the population. There are lots of methods that say, if you know a bunch of other things about the about your units that you're studying, people, businesses, then there are methods to use the statistical relationship between those auxiliary characteristics and your study variable in order to reduce standard error even further on the statistics that you're interested in. So that's why that's important. Okay, so here we get to the estimating equations. So we're going to consider some population parameter that is a function of sort of every unit in the population. With this estimating equation here, so it's just an average that is a function of our possible mean, median, whatever else. And the way that these estimating equations are defined is such that most of the time you can get back the statistic that you're trying to compute by setting that average there, the estimating equation, to 0, and then solving for theta. There are some statistics where we can't quite do this, so we have some kind of asymptotic limiting argument to still make them work for things like quantiles. But for most statistics, you can just set them to 0 and solve. Now, why do I want to find an average that when I set it to 0, I get back the statistic that I'm computing? Well, it's because we can use that average to calculate things like standard errors and also to study convergence properties and so on that are kind of very useful for us as statisticians. It's exactly the same story for a sample statistic. So here we just have a sample estimating equation that's that we can set to 0, solve for theta, and obtain the statistic that we're interested in. And here it's the sample estimating equation because we're going to set the summand to 0 for units with no observed variables. And here's why estimating equations are useful, because we can do variance estimation with them, amongst other things. So we're going to look at probabilities, expectations, and variances under the sampling design that is conditional on any random mechanism that might be driving underlying incomes in the population, for instance. So we would call that underlying mechanism the superpopulation. Here, when we subscript by little p, we're just talking about the design. And with no subscript, we're going to be talking about both the design and the superpopulation. Now, if your statistics converge to some value and your estimating equations, which are averages, so we have a law of large numbers, they converge to some function, then we can, if we estimate the derivative of the estimating equations and we estimate the variance of the estimating equation, we can do a Taylor series argument to obtain the variance of our sample statistic under the design. And that will get us the standard errors and the p-values for our scientific study. But if that variance is also the function of parameters that define the random mechanism that we use to select the probability sample, then this is the function we will optimize in order to decide how we randomly select our units. If we also have an estimate of the variance of the estimating equation at the the superpopulation level. That is the variance of the estimating equation for this or under the mechanism that drives actual incomes, for instance. Then we can add those two variances together in order to get the variance, the unconditional variance that accounts for randomness from both sources, both from the underlying superpopulation, but also from the randomness that the ABS, for instance, injects into this system through our random sampling. And I've put on this slide formulas that you can use to solve for those previous quantities here in order to get those standard errors, with the exception of V hat S here, which varies considerably based on the survey design that you're, or the set of survey designs that you're working with and that you're optimizing. We can use find estimating equations for an enormous array of statistics. So suppose we've got some CDF here that's some combination of a continuous component with a density and a discrete component with a mass. Then if we kind of look at the estimating equations of a whole bunch of statistics here, we can kind of get a sense of how broad this approach can take us. So for means, quantiles, Gini indices, linear regression coefficients, and maximum likelihood estimators, you can see on the right there, you can take those formulas and substitute them into the appropriate places on the previous slide, and out will come a formula that you can use in order to compute your standard errors, or in order to compute a variance that you will then optimize to produce a sampling design and therefore an efficient, affordable, cheaper survey to get you statistics with lower standard errors. Okay, so then the question is, how do we do the combination between the probability sample and the non-probability sample if you're an external microdata user? So if you're logged into our data lab, for example, then when you're accessing ABS data that's related to a survey, you'll have these survey weights. And when you use those survey weights to compute weighted means, weighted medians, and so on and so forth, it will correct for the bias introduced by the sampling selection mechanism. Then if we're integrating, and in the interest of time, I might kind of speed over this a little bit, but basically if we're integrating from a probability sample and a non-probability sample, you can use these weights here to calculate statistics in a way that gets the best of both worlds. So we have these weights, our statistic is computed according to these weight variable pairs, and we can use replicate weights for variance estimation that are provided for some ABS surveys that allow you to do variance estimation from the perspective of the design. If you're an NSO statistician and you're not external to the ABS, for instance, then the situation is a little bit more complex because we need to come up with the survey weights. Now, if it were only the random sampling selection mechanism that we kind of know, if it were only that affects the sample that we get, then we'd be fine, we know what to do. But in reality, there's non-response, so that's like selection bias. We ask people to participate and they don't respond. There's measurement error, there's linkage error, and so on. But we can correct for those using statistical models. So how do we use the formulas on the previous slide in order to, for this case? Well, we just stack the column vectors. So we concatenate all parameters into a single column vector theta. We concatenate the estimating equations, and hey, presto, you can now use the previous formulas in order to compute your standard errors, which end up being variance covariance matrices. And now you can pick off the element on the diagonal that relates to, that gives you the variance for the statistic or statistics that you're interested in. And then we can optimize this to produce sampling designs that are A, tailored to the statistic of interest, and B, account for sampling variability of the model parameters, which is very important because this is what tells you whether or not you're overfitting your modeling to inject more variance into your statistic than could be corrected by, then could be compensated by corrections to these errors in the form of bias, for instance. And we've written a paper where we kind of illustrate this in a case study. And if you're interested, come talk to me and I can give you that source. I won't go through the simulation and the real data example in the interest of time, but basically, when we run a simulation, we get the asymptotics that we expect from our theoretical results, both in terms of the bias of the sampling distribution and also the variance. And for the real data example, we see that the teal estimates here are closer to the purple kind of ground truth census results than the alternatives. So what have we done? We've explored a general estimation method that combines data from two different kinds of samples. We correct for coverage bias or selection bias in the non-probability sample to get asymptotically unbiased statistics with a lower variance than just using the probability sample, just using the survey. And we can obtain variance estimators that we can optimize to produce an efficient survey design, or that we can use to produce p-values. And we can also incorporate corrections to other biases like survey, non-response, and measurement error, with variance estimators that account for variability due to these corrections. Thank you to all of my colleagues who have provided feedback on this work and improved it. And that's it from me.
Hi everyone, so my name is Chris Mann. So I'm in our Data Access and Confidentiality Methodology Unit, as are a lot of the ABS delegation here today. Ryan's kind of a special extra guest here, but very thankful for his assistance. So I'm just going to be talking about a problem called tabular suppression, and because of the team I'm in, this is related to confidentiality, which is about protecting people's privacy or protecting the privacy of survey respondents at the ABS. So very, very simple example. Suppose we had this table of turnover from 24 businesses across 5 regions, and kind of see there's a problem here that in region D, there's only one business there. That area is a little bit off point as well. The problem is if we release this table as is, even if we don't release the contributors column, then we're basically saying what that one business is making in turnover, and there's a lot of rules about what we can do with the data we collect, and one of them is we can't release something that just directly says this one unit has this value. So what we can do is we can just take it out of the publication, and hopefully all the bright minds in the audience today can realize that there's a problem, that there is still enough information left in the table to just, like, it's maths, it's not even, it's like 3rd grade or something. You just subtract 1 from the rest. So what we've got to do, there's a lot of ways we could treat this, but probably one of the easiest things is we just suppress something else in the table. So we just pick another region, the region E, and suppress that as well. And so now if someone does the same trick of subtracting one thing from the others, they get the combined value of D, regions D and E, which is 4 businesses, sorry, I don't even know my own numbers. But hopefully that's enough to give enough protection that we can then say, okay, that's safe to release. Cool, so if that was all that we worried about, then I probably would not be talking here today. ABS tables are a little bit bigger than this, and they're also a little bit bigger than this, but we'll just kind of scale up to see where the complexity starts creeping in. So suppose there's just some table, maybe it's counts, whatever it is, these are all made up numbers anyway. But suppose that all of those boxes I've marked there with 1s and 2s in them are things that we say we can't release for whatever reason. So maybe they are counts as 1 and 2, and we consider that to be unsafe. So once again, not publishing those, that's fine. But again, now we've got 2 directions that you can do maths in, which is twice as many as 1s. Great. So I was done. But yeah, so it means that, you know, when we're adding more suppressions to the table, we have to be thinking about the dimensionality of it all, and maybe we suppress these extra ones there. I don't know. If you look, it seems like there's at least 2 suppressed cells in every row and column, so maybe that's all we need to do. And that's where we start doing the actual maths. So, you know, are these suppressions actually protecting what we want to protect? So are they hiding those values that we said were unsafe? And are they the best option? Like we could suppress something else. I'm sure there's other options there. At the very least, we could just not publish the entire interior of the table. That's probably going to work, but also means we're not releasing a lot of really good data. So what does it even mean to say these are valid suppressions and that they're the best suppressions, and best is optimal, and that's probably why we're talking here. So there's a couple of directions we can approach this problem, and one side is what if I'm actually looking at this table with suppressions in it, and I'm the person who wants to know what's behind that NP, what's the actual number under there. And one way to do that is with a linear problem or linear programming problem. So because the tables they add up, and for the most part, most ABS tables, no matter how complicated they are, the basic structure is linear relationships. So linear programming seems to be a good idea. What we can do is say, what is the biggest number that could go into one of those suppressed cells if I tried to fill the whole table up with values that still added up correctly? And probably, you know, if I said there were counts, then they have to be non-negative. Maybe I know that nothing can be bigger than some upper bound or whatever. So I can just kind of put that all in. And as far as optimization problems go, that's pretty nice. It's like 4 lines really. I mean, obviously there's a lot of repetition and matrices and stuff in there, but as far as like you've seen much worse, I'm sure. So this is basically saying what could an attacker figure out, and you can maximize the value, you can minimize the value. That gives you a range or an interval, and we can say, well, maybe if that interval is empty or only has the one value in it, which is probably the true value, or maybe if that interval is like a little bit too small for our liking, that's considered not properly protected. And that's essentially what we do. So we set some desired limits. And so this is the other end. We know what the adversary is doing. Now we know what we need to protect against. So we set some limits, and then we just throw suppressions at the table until we reach those limits, and we say we're good. And then we say, well, could we have chosen better suppressions than just throwing them at random? And obviously that is a minimization problem of utility loss. So we have set some kind of cost function. I am leaving all of the actual model details out here because I do not have any time to go through it, but it's all very interesting stuff. But yes, you can kind of say, we want to suppress as few cells as possible. We want to suppress smaller values in cells where possible, something like that. We set a cost related to that. There is a full formulation for this, which is a mixed integer linear programming problem. The classic formulation of which is really pretty and really easy to understand, and also one of the most inefficient things I've ever seen. And so obviously when you have a horribly inefficient model, you look at ways to turn it into something that's actually a bit more viable. And so Shetty and Salazar in 2001 have this Spanners decomposition approach, which at least one person has called really cool. Not me, but someone who I definitely respect in their opinion. But that's still an integer problem. There's also linear programming approaches to do it, which give away the whole trying to find the best option possible and just say trying to find something that's decent but actually runs in a human amount of time. And so we're actually looking at a piece of software from Stats Canada called gconfid, which implements one of these models as well, which I personally think is very cool. So I'm keeping this nice and short to make sure there's plenty of time for Joseph and for questions. So this is based on my last slide. But yeah, so we are looking at all this stuff. It is all very interesting and exciting. We are facing challenges. We are still building our optimization capability. So both in terms of the people, we have people who know optimization theory. I kind of self-taught myself the bits on the previous slides. I still don't think I've got it right. But we do, we have some good people, but we also have a lot of people who know maths and statistics, don't know optimization. So if you're looking for a place to work, definitely you can come and join us. Although this is the second part there, the software. Our IT environment, because we have security issues, maybe you don't always have a good IDE and a solver and the ability to put actual ABS data in the same place at once and then run it. We are working on ways around that and actually improving that, but it is one of the challenges we're facing at the moment, so that's been fun. We have the problem that ABS tables are big. Probably not as big as the biggest optimization problem people are running these days, but they seem big to us, and they're also very complicated. You've got like 5 different variables and they have hierarchies, so you're not just adding up in these directions, but actually this value adds up to this value, adds up to this value, adds up to this Australian total or something. Like I said, it's an MLP, so it is NP hard. Fouché and Salazar did say specifically, that's tied to an actual NP hard problem, so there is no getting around that. And even at the moment, the LP versions, they're running a little bit slow, and C.1, maybe we haven't coded them the best way, maybe we are not running them in the best environment. We haven't tried throwing everything at our disposal at it, but certainly still a little bit. But yeah, it's kind of in that space where we're very excited about it, and we're hoping to fix all those things or find people who can help us fix those things, which is why working with Optima has been really great as well. But yeah, that is kind of all of what Tabular suppression is about.
So my name is Joseph Chen. I'm like Chris. We call ourselves DACNU. I know it's easier to say data access and confidentiality methods. So like Ryan mentioned earlier on, that we really like to explore making use of optimization approach. We I guess we all try to solve different problems. So Ryan's problem is trying to think about what's the optimal sample size, give me the biggest bang for my buck. And then our problem is try to make the balance between the data utility and protecting of providers' confidentiality. So I'm gonna sort of describe a bit of the research that we did in relation to help the ABS making our data more accessible. So in 2022, we had the new bill that passed that tried to encourage the public sector data sharing. So that will help the researchers to, I guess, answer some very have richer information to answer questions like how well the government has been running their programs, or opportunity to really understand can we solve some wicked policy problems like indigenous disadvantage, or some of the sort of very hard problems. But obviously, with more information, there's always comes a challenge of how we actually ensure the providers' information are probably protected. So the ABS has a service called the Data Lab, where we host some really rich data assets. The researchers can come in and they can analyze the output. And then we have a process to ensure the statistical output we publish out of the Data Lab is safe. Currently, the process is manual, unfortunately. So we try to think of the way to, can we introduce a way to make this safer going forward? And as you can see from the chart to the left, the service demand is just increasing over the year. And, obviously, it would be good to look for ways to really managing the difference in risk. I won't go through all the ins and details about the risks, but yeah, so basically this particular research is looking at how we sort of, I guess, improve ABS provide our service. So I want to sort of quickly go through the ABS perturbation methodology. That's our ABS invention. So basically, there are two main components in ABS perturbation methodology. On the right-hand side, we call the Selkie method. That's sort of how we ensure the statistics are consistently published and consistently protected. And then on the left-hand side is we call the entropy maximization. Basically, we think about, well, how much noise we add to the output. And today's talk, I'm sort of want to focusing on the entropy maximization. So, oops, sorry, wrong way. All right, so the way we improve the entropy maximization is we try to introduce a differential privacy framework in the design of the noise. So, I want to sort of give a very high level introduction of DP. I'm definitely not an expert here, like Chris. We're still learning how differential privacy works. So what it is, what's DP? So the DP is kind of like a measure the privacy risk in the respective of the output. So typically, as a statistician, we often worry about how safe is the input. So we often think about unit risk. So the biggest innovation in the differential privacy is really, instead of thinking about input, you look at how well the mechanism protect the output. So the easier way to think about this is, the differential privacy is, imagine you try to spot this sort of two blur pictures. So if you do your mechanism right, and this, so imagine those two blur pictures, two tables they've been protected under some mechanism. So if you do your job right, you shouldn't spot the difference. There's one little minor difference between these two blur pictures. And sort of and then when we say, so when you say that, I think you can probably spot it. So obviously I didn't do a very good job, but anyway, and then there are a lot of different frameworks. So a particular framework we explore is called the epsilon delta differential privacy. So when we say a particular mechanism meet that framework, it's basically satisfied that inequality I showed there. So here there's two parameters in play. So epsilon's basically known as the privacy budget. So basically think about it as how blurred you want the picture to be. The delta, it controls what we call the failure rate. So basically what it says is that, well, it basically controls how, is this blur, have you blurred enough of the picture to make sure the output is safe? Right. So I want to sort of run through a very simple example of what we think about calculation of epsilon and delta. So look at those sort of two identical distributions. There's like a noise distributions. So the green line is just the blue distribution scale up by by a factor. And then when we talk about two neighboring distributions, so if you think about you want to protect your output, you both add in noise, and they all come from some kind of distributions. And this is two neighboring distributions. And when we talk about when there's a delta, basically when we say, well, when we overlay these two distributions, there's a bit that doesn't cover. So the big picture out of that, what I want to show you is basically, you worked out the bit that doesn't cover when you shift that distribution, and that's basically what it means by the failure rate. So in this basic example, is delta 1 and delta 2. So what we did, so our approach, as you can say, we sort of took the entropy maximizations is sort of our principal method, or the method we used in the past. Professor Seti and myself, we published a paper last year, basically introduced a particular form of Lagrangian optimization process. And we were able to prove that under the symmetric supports that you are able to achieve a particular a particular epsilon. And we also came up with a way to I guess derive that delta and to meet the variance constraints as well. So we took what we did. So Eamon, my ABS colleague Eamon and I sort of took that work and we kind of built to expand that to when we talk about asymmetric support is when the noise is not -5 to +5, or it's sort of then that's could be -3 to 7, or so that's what we did, and that's a particular form of the Lagrangian we solved. So what's I'm moving? Sorry, can't go to next slide. Sorry. So this is the algorithm we developed. So it turns out, oops, sorry, I thought, yeah, that's right. Sorry. Yeah, so we basically developed two sub-algorithms in solving that problem. And then we kind of make it like iterative steps. And we also implement a sort of parallel processing to sort of do an exhaustive search rather than just a simple step down. And then we were hoping to, I guess, sort of hear from some thoughts about maybe this might not be the best way to formulate the problems. So give you a very high level intuition of how our algorithm works is basically we need to control so that we want to make sure we achieve a particular epsilon, like there could be a target epsilon of 0.5 in this example, and you really want to achieve zero bias, so all your noise end up to won't affect your final result. And so that means so it's quite, I mean, it can't be exact to 0, 0, but it's small enough. So it's sort of, to meet the target. So here are some of the questions that we still try to answer. Like, have we, we always keep asking, have we been imposed appropriate constraints? Is this the best way to think of the trade-off between the utility and protection? Are there more efficient processes we should have thought about? Like, hopefully, sort of targeting two objectives at once. And can we sort of formulate the problem jointly rather than like what we're currently doing at the moment, sort of solving it sequentially? And are there other things we should consider? So yeah, with that, I will, and this is a reference list. So open it for questions. Thanks.